Welcome to part one of conditional and logic programming. In this section, we're going to cover a variety of things, but it's divided into two parts, and I'll cover the items that are going to be discussed in this section on the next slide. In part one of this section, we're going to cover Boolean variables and also how to build Boolean expressions using both relational operators and logical operators. Relational operators you'll find cover less than or equal, greater than or equal to, not equal to, and equal to, while the logical operators that we'll discuss are the and, or, and not operators. We'll talk about how these different operators fit into the operator precedence, especially when combined with the other operators we've learned so far, and then we'll look at an example of how these are used. In Java, there are 8 primitive data types. The 4 integer types, byte, short, int, and long. The 2 floating point types, float and double. Char, which is used to represent a single character. And boolean, which we'll discuss in detail in this section. So, as I said, the first 4 are used to store integers. So, whole numbers, positive, negative, including 0. The float and double are used to store floating point values or numbers with a decimal point and values after the decimal point. Chars for single characters, and boolean is meant to store values of either true or false. And in fact, in Java, there are keywords true and false, all lowercase because all keywords are lowercase, for that. So you can create a Boolean variable in the same way you'd create any other variable. Use the type of Boolean, then name your variable using the rules of naming, and then use the assignment operator of equals to assign it a value. You can assign it a literal value of true or false, or you can assign it the result of a Boolean expression. And Boolean expressions are used to create either a simple or a complex equation that at the end of its evaluation, the result of that equation will be true or false. And we're going to learn about 2 additional groups of operators in this section, relational and logical. And we'll learn how we can use those to combine them to make expressions that will result in true or false. And then that will allow us to do the things that come in the second section of this, which is create conditional statements. And we'll go over those in more detail in part 2. As mentioned on the previous slide when talking about the Boolean type, we often need or use an expression on the right side of the assignment equation to assign a value of true or false to a Boolean variable. And the relational operators are one of the ways that we do that. There are 6 relational operators that we're going to look at. And you can see in this table, the first column demonstrates those operators in a way that you might be used to, how they look in a mathematics textbook, for example. We have the first one is less than, and it's the same in a math textbook and in Java. The next one, though, is less than or equal to, and in a math textbook, we have the less than symbol with a line under it to represent that. But we don't have a way to represent that in Java, so we put the less than symbol with the equal symbol next to it to represent less than or equal to. Then we have greater than or equal to, and not equal to. And you can see the not equal to that we're used to is the equal symbol with a line through it, but we don't have that symbol in Java either. So we use the exclamation point, which is often used to represent not, and combine that with the equal symbol to give us not equal to. Now, the rest of this table shows us some examples, and then what the result, the Boolean result, would be of each of those examples. So, 1 less than 2. We know that 1 is not less than or that 1 is less than 2. One less than 2. We know that 1 is less than 2, so we know that the result of that is going to be true. On the next line, we have 1 less than or equal to 2. Well, if 1 was less than 2, it's definitely less than or equal to 2, and that will be true as well. 1 greater than 2. Well, if it's less than 2, it's definitely not going to be greater than 2, so that would be false. 1 greater than or equal to 2. Again, if it's less than 2, it is not going to be greater than or equal to 2, so that's false. 1 equal to 2, that's false as well. And then finally, 1 not equal to 2, and the result of that is true. And again, the value of true or false is what is stored in the Boolean variable if we have one of these expressions on the right-hand side of our assignment operator. And what you'll find as we go through this chapter is that we can combine these using logical operators into more complex statements. We can use variables on either side of the comparison operators as long as they have numeric values in them. And we'll use these in a variety of ways. And I would pay close attention to the examples in the textbook and the different examples you see as we go through the slides for this chapter. And now we're going to add logical operators to this. Now, with our relational operators, we had to have a numeric value on the left or right, and we compared them, and the result was true or false. Our logical operators deal with Boolean values. So our first operator here is unary, so it means it only has a single operand directly to the right of it, and it is the not operator or exclamation point, and it's a logical negation. So if you have a Boolean value, we'll look at the truth tables on these on the upcoming slides, so we'll save that for a minute. Our next three are all binary, so they have an operand on the left and on the right, and when they're compared, we can get a result of true or false. So the second one there is double ampersand or and. The next one is the double pipe symbol, which is above the enter key on your keyboard, and that's an or. And then the last one is the caret symbol, which is above the 6 key on your keyboard, and that is exclusive or. And we'll talk about how each of these works on the upcoming slides. All right, now we're going to look at truth tables for our logical operators. And on this slide, we have 2 truth tables, one for the not and one for the and. And so the not is a unary operator, so it has just one operand it works on. And a truth table works like this. We have a variable that's our operand, in this case p. You'll see that since the and is a binary operator, it has p1 and p2 that it's going to operate with, because one has to go on the left, one on the right. But the way the truth table works is that for the operands, the variables, we're going to test it for every possible value. So when you only have one operand, as in the case of a not, you have just 2 possible values, true or false. And so we can see that once we apply the not operator to true, it becomes false. And if we apply it to false, it becomes true. So it reverses the standing of that operand. For the and operator, we're going to have 2 variables, and so we have to have all possible combinations of true and false. So we have in our first column false, false, true, true, and then when combined with the second column, we're going to vary that by false, true, so that the combination is both false, only the right-hand side is true, only the left-hand side is true, and both are true. That gives us all 4 combinations for these 2 values, and we're going to see what the results are now. So if both are false, the result will be false. If one of them is false, either the left or the right, the result is false. And so an and is only true when both values are true. The left side and the right side of the and symbols will give us a value of true. And notice I've highlighted the true result for each of these on the slide. On this slide, we have two truth tables, our OR truth table and exclusive OR. So let's start with the OR. Now, both of these are binary, so you'll notice we have P1 and P2. We have all the combinations, both false, left false, right false, and both true. And let's see what happens when we combine those two variables with the operator. So when we combine them with the OR, you'll notice that when both are false, the result is false. However, with the OR, only one of the items has to be true in order for the result to be true. So this occurs for the right-hand side true, left-hand side true, and both true. So if there's a true value in there, the result of OR is going to be true. Now with an exclusive OR, it's slightly different, and the difference is that only one of them can be true. So that means if the right-hand side is true or the left-hand side is true, the result of an exclusive OR will be true. However, in the case where both are true, an exclusive OR says no, the result of that is false. It's a little odd, but it makes it, it gives it a reason for existing, because if it was the same as OR, we wouldn't need it. Let's take a moment to discuss short circuit operation. When you're evaluating the and or operators in Java, they operate in a short circuit fashion. And what that means is that when you're evaluating them from left to right, the expression will exit as soon as it is able to determine that it knows the end result. So what does that mean? For P1 and P2, Java's first going to evaluate P1. It is not going to look at P2 if it doesn't need to. And so what are the cases where it wouldn't need to? Well, if P1 is false, then there's no way for this entire statement to result in true, because as we said in our truth table, an and expression is only true when both values are true. So if we check P1 and it results in a false, then we don't need to look at P2 and evaluate that. For the OR statement, remember that we said that it's going to be true when either left or right is true. So in that case, if we evaluate P1 and it results in true, we don't need to evaluate P2, because if it were false, the statement would still be true because the left side was true. And if it was true, it would also be true. So as long as the left side is true, we don't evaluate P2. Now, the reason it's important to mention this is that P1 and P2 may not simply be a value. It may not just be a variable that has a value of true or false. It can be an expression that evaluates something, that assigns a new value to a variable, uses the increment or decrement operators and changes that value. And that's important because if P2 is such an expression and it doesn't get evaluated, then that expression is not going to execute and the value does not change. So if you are writing something where you're expecting a value to change and a short circuit occurs, it's never going to touch or look at the right side, and so what you're expecting to happen may not happen. Because we introduced multiple operators in this section, I want to touch base on the overall operator precedence in Java. If you look at this list, it goes from top to bottom of operator precedence. Now, the only thing not included on here is parentheses. Parentheses can change the ordering of any of these because they take the top priority. But there are things we've introduced, and so let's look at those. We have the typecasting we've seen in previous chapters, so where you would put like int in parentheses in front of something to convert it into an integer. We've seen plus and minus. That's unary, so it's like making a number negative or a variable negative. We've seen that in previous chapters. We've seen multiplication, division, and remainder. We introduced the not operator, which has a higher precedence than those. We have binary addition and subtraction. Introduced that early on. Our comparison or relational operators were introduced this chapter. And the equality and not equal operators were also introduced, and they're just one precedence level lower than the less than greater than operators. And then we have and or, and exclusive or. Notice there's a single and a single pipe for or. We didn't talk about those this chapter. We talked about the double ampersand and the double pipe for or. And those are the short circuit versions, and we mentioned that in a slide in this section. Notice at the very bottom is the assignment operator. This is important to remember because we often have an assignment statement and we have an expression on the right-hand side, and we have to remember that everything in that expression on the right-hand side needs to be evaluated before the assignment is executed. So that's very important, but this is a good reference slide to refer back to when you're setting up equations or expressions to make sure that you're setting things up in the right order and that you're utilizing parentheses where needed. Because if you need for something to happen first, but its precedence is lower, like if you need addition to take place before multiplication, you can wrap the items you're adding in parentheses so they'll take place first. It's very important to understand this and internalize this as you're setting up expressions in your programming. At some point, you may need to calculate whether or not a specific year is a leap year. If you're building a calendar, for example, you're going to need to know whether to add that 29th day to February. And so this is a formula that's demonstrated using some of the math operators and logical operators that we have learned in this chapter so far, and we are going to use those to calculate whether or not a specific year is a leap year. Now, the rule for figuring out whether something is a leap year is that the year is divisible by 4. That's the one that everybody's used to. However, there's a couple of exceptions. The first exception is that if it's divisible by 4, but not divisible by 100. However, it can be divisible by 100 if it is divisible by 400. So there are 3 instances every 400 years where a year is divisible by 4 and it is not a leap year. So, for example, the year 2000 is a leap year, but the year 2100, 2200, and 2300 will not be leap years. 2400 will be, but everyone in between those that's divisible by 4 will be leap years. So how do we code this? Well, first we have 2 things that we want to check. The second thing is simpler, so we'll look at that first. Is the year divisible by 400? Now we have this awesome math operator called the modulus or remainder operator, where we can mod something by the year by 400. And if the result of that is no remainder, meaning it's equal to 0, then we know it's evenly divisible by that amount. There's no remainder left over. So if we want to know if something's divisible by 400, we say year remainder 400 is equal to 0. And if that evaluates to true, then we know that our number is divisible by 400. The left side of this is we have to test if it's divisible by 4, but not divisible by 100. So we know how to test if it's divisible by 4, same way as we did by 400, except we're doing year remainder 4 equal to 0. If that's true, then it's divisible by 4. Now, if we say year remainder 100 not equal to 0, then that tells us that it is not divisible by 100. And that's what we want. We want it to be divisible by 4, and we want it to be not divisible by 100. So if the left side, year mod 4 equal to 0 is true, that means it's divisible by 4. If the right side, year mod 100 not equal to 0 is true, that means not divisible by 100. And so both of them being true is the result we're looking for, and we want it to evaluate to true if they're both true. So we use the AND operator, because that's the only time that it'll be true is if both the left and the right are true. Now, we don't care if the result of that is true or if we're divisible by 400. Either one of those are fine, and we know we have a leap year. So if either the left or right being true is okay, then we'll use the or for that, and that'll allow us to have a positive result or a true value if either the left is true or the right is true. So take a look at that, run that in your code, and do some tests on it and see what you come up with, and have some fun with it.